We are facing great challenges. With our need for energy and the industrialization, we are altering our world. The climate of the planet we live on is changing, and we are starting to feel the repercussions of our actions. The average temperature is rising, which leads, amongst others, to more frequent wildfires or devastating floods. Other challenges of our time include fighting for gender equality, ensuring healthy lives and well-being for all, as well as providing enough food and clean water for everyone. These and other challenges are summarized in the list of 17 global goals for sustainable development. To prepare future generations for such challenges and to help them and us to achieve the aforementioned goals, we need good education for everyone. This is essential in many fields, for example, natural and social sciences, engineering, medicine or finance, and especially mathematics and mathematics education, as we are going to see. Fortunately, living in the so-called information age, we have more knowledge available than any generation before us. At the tip of our fingers, with any device that can connect to the internet, we can find almost any information we might need. This, however, challenges us who work in education. For example, memorizing formulas becomes less and less important. In turn, finding and selecting appropriate information and evaluating it is becoming increasingly relevant. The availability of digital tools will drastically transform learning settings. All around the world, mathematics classrooms often look like this. The teacher demonstrates an algorithm, a procedure, or a rule. The students, who are seated in rows, work individually in exercises to memorize and train what they have been told. And most often, as studies like TIMSS or PISA indicate, this way of teaching is not very effective. After written examinations at the end of the respective teaching units, students tend to forget what they have learned. Additionally, students seem to learn mostly skills for solving routine tasks instead of mathematical competencies like arguing and reasoning, modeling, or problem posing and solving. But what do students need to be able to successfully face the challenges of our time? And what do teachers need to help them gain such skills and competencies? There are, for example, the so-called 21st century skills. That is a list of skills, abilities and learning dispositions that have been identified as being required for success in our modern society. Looking at this list, we instantly recognize the importance of mathematics education. For example, critical thinking and problem solving is part of mathematics curricula all around the world. Mathematics encourages a special way of communication, and information as well as media literacy require statistical knowledge. In this presentation, I will address some of the skills for students and teachers that I think are necessary for the future. As this is a scientific conference, I will additionally focus on research methods to gain access to the mentioned skills and constructs. This is important for us as researchers so that we are able to better understand the process of teaching and learning. As we have seen, the challenges are manifold, and in this presentation I want to address two affective and two cognitive challenges. Starting with epistemological beliefs. So what are epistemological beliefs and why are they important? Epistemology is a branch of philosophy dealing with the nature and justification of our knowledge. Asking questions like, what is knowledge? How is it being generated? How certain is it? The research on beliefs deals with what philosophers characterize as propositional attitude or mental state of having some attitude, stance, take, or opinion about a proposition. So if you take both together, we come to epistemological beliefs that Hofer and Pintridge defined as beliefs about the nature of knowledge and knowing. So why is this important? Looking at this pandemic we are still living in, example A, Arthur wants to get information about wearing protective masks. Does this protect him or others, or is it a restraint? Do they really work? And when we look back at last year in March 2020, a lot of scientists said that masks are useless. And then 2 months later, they suddenly said everyone should wear a mask. So who should Arthur trust? People like Anthony Fauci, who says everyone should wear masks, or people like Donald Trump who say, I don't believe in masks. Another example from natural sciences. So far, Bianca, my example B, has been familiar with experiments in physics classes as follows. The teacher shows a phenomenon, and then in class, they develop an explanation or a theory. And Bianca does not think of experimentation as goal-oriented. She has no idea of hypothesis testing, experiments, or theoretical physics. So for example, this experiment by Rutherford, where he showed that atoms have a nucleus. Bianca would ask, how could you possibly come up with that? Was that a happy coincidence? And my example C, relevance for mathematics. Think of Christina as a mathematics teacher. From her own days at school, she knows the mathematics of rules in red boxes. So the teacher presents a procedure or a rule, then put a box around it, everyone should copy it, and then exercises are given to train this procedure. And during her time at the university, she experienced how mathematics professors work. In all the lectures she had, the content was presented in a deductive order. So they were given axioms and then theorems, proof, theorem, proof, theorem, proof. So she experienced mathematics in a very deductive way and always with someone knowing everything to know. So in her classes, she copies this. She tries to explain everything as well as possible to the students, and then they have to practice it. She never experienced mathematics as an activity where you can explore yourself, where new knowledge is generated or something similar. So how is research on this topic done? This started in the 1950s and 60s with interview, and interviews are still being conducted today. A very famous example is this Venus form by Letterman, the Views of Nature of Science questionnaire. However, since Marlene Schommer introduced her questionnaire in the 1990s, the standard method of measuring beliefs and epistemological beliefs have become these self-report Likert-Scale instruments, where you get statements and then you agree or disagree to those statements. For example, here are some items from the Schommer study. The only thing that is certain is uncertainty itself, or being a good student generally involves memorizing facts, and you agree or disagree to that. And other studies like the German coactive study also used this kind of instrument to measure beliefs. However, there is a lot of criticism regarding these Likert-Scale instruments. For example, the social desirability, reliability, and validity. Those instruments tend to represent the positions of the test creators and not necessarily those of the people who take the test. They are designed for large samples, allowing little individual insight or meaningful interpretation. It is difficult to distinguish general from domain-specific beliefs. And most often, they just look for positions, and you cannot be sure how reflected those positions are. Going a bit into detail, social desirability is a huge problem when people consciously or unconsciously give answers to look better in the eyes of the researcher. Regarding reliability and validity, we see, for example, this study by Zakaria and Musiran, where about 85 or 90 or even more % of the participants said that students should be encouraged to justify their solutions. And they all agreed that learning mathematics must be an active process, but the same 96% said that mathematics should be taught as a collection of skills and algorithms. To solve math problems, you have to be taught the correct procedure. So these answers are a bit contradictory. Sometimes context is missing. Statements in such instruments are often very general. So what context or content do you think about when asked about the certainty of knowledge? Do you think about the Pythagorean theorem, which is very certain, or Andrew White's proof of Fermat's last theorem, which is still understood by only a few people in the world? Or when you are asked about learning settings, how calculus-based oriented are they? Do you think about arithmetics, algebra, analysis, or geometry? This really matters, but these items are not specific what they address. There are alternatives to such Likert-Scale self-report instruments. For example, you can still conduct interviews, but this takes a lot of time, effort, and money. So other instruments have also been developed. For example, rank then rate instruments that have been introduced to mathematics education by Safruddin Noor. You also are given statements and you should rate them on a Likert scale, but before you do so, you have to rank them. You have to put them together, think about which of these statements is more important than the other. Then you have to rate them in consideration of the others. So for example, you give them those ranks. This is the most important, the second and the third. And then your rating has to show this ranking. But you can still differentiate. Is the first and the second very close to each other? For example, 7 and 6, or is the first far more important than the second? And these instruments have been proven to be better regarding validity and also social desirability. In a study by Safruddin Noor, we compared such rank then rate instrument with a classic Likert scale instrument and interviews, assuming that interviews give us the best way of measuring students' beliefs, or in this case, teachers' beliefs. And we could show that the rank then rate instrument provided us with results that were more similar with the interview than the classic Likert scale instrument. Okay, let's put the spotlight on a second affective challenge, mindsets. The theory of mindsets has been introduced by Carol Dweck, and she says, the power of yet. I heard about a high school in Chicago where students had to pass a certain number of courses to graduate. And if they didn't pass a course, they got the grade not yet. And I thought this was fantastic, because if you get a failing grade, you think, I'm nothing, I'm nowhere. But if you get the grade not yet, you understand that you are on a learning curve. It gives you a path into the future. Mindsets are the way we think about abilities and talents, and they are on the spectrum between fixed and growth mindsets. There has been a lot of research on mindsets, and for example, when you have fixed mindset, you think that abilities are innate and unchangeable, whereas when you have a growth mindset, you think that abilities can be improved through practice. People holding a fixed mindset think that failure is permanent, whereas growth mindset people think that failure is a chance to learn. Feedback is often regarded as a personal attack by people with a fixed mindset, or as a chance to improve by people with a growth mindset. People with fixed mindsets tend to choose easier tasks because it doesn't matter what they do. They show less effort and give up easier, whereas people with a growth mindset tend to choose more challenging tasks. They work harder, they work hard to improve themselves, and they are easier to accept challenges. People with a fixed mindset often focus on measurable outcomes, grades, whereas people with a growth mindset focus on the process or the journey to get somewhere, to learn something. And especially people with a growth mindset are far more successful in school and university and in their jobs. And the good message here is that mindsets are developed by experience and can be taught. So people can learn to have a growth mindset. This is not easy, however. So for us as teachers, it is important to create learning environments with positive feedback culture and a positive way of dealing with mistakes. We need to give appropriate feedback and act according to it. For example, we shouldn't praise intelligence. You are a good student. you are a very intelligent student, but we should praise effort and strategy. You did very well. You showed a lot of effort, so that students can see and learn that when they put effort into something, they can get better. So whenever someone says, I cannot do it, then we should say, okay, you cannot do it yet. So you can learn to do it. And this really makes a difference. Looking at research on mindsets, I found a study from Indonesia, but this is typical for research in this area, that mindset often is researched with, again, these self-report Likert-Scale instruments. And we've already seen that this should or might be criticized. So there is a lot of room to improve on research in this area. So maybe some of you are going to do this and invent new methods how to do research on this. Looking at the first example of a cognitive challenge, problem solving. So what is problem solving? Alan Schoenfeld said, let me begin with a definition. For any student, a mathematical problem is a task, A, in which a student is interested and engaged, and for which he wishes to obtain resolution, and B, for which a student does not have readily accessible mathematical means by which to achieve that resolution. So this is very important. Problem solving is about solving tasks for which you do not have a procedure or an algorithm. This implies that tasks are not problems in and of themselves. It depends on the people, on the solver, whether they know an algorithm or not. And most of the textbook or homework problems, especially in the English language, everything is called a problem. Most of these problems assigned to students are not problems according to this definition, but just exercises. So think about problem solving. We really need challenging tasks. Why is this important? There are many reasons why problem solving is important for our future, dealing with the challenges we face, but also for mathematics. Paul Helmers, a famous mathematician, once wrote, what does mathematics really consist of? Axioms, theorems, proofs, concepts, definitions, theories, formulas, methods. Mathematics could surely not exist without these ingredients. Nevertheless, none of them is at the heart of the subject. The mathematician's main reason for existence is to solve problems. And that, therefore, what mathematics really consists of is problems and solutions. So if we want to teach our students about mathematics, and not just calculus, then we need to teach them how to solve problems. And when we think of problem solving in learning contexts, we can learn about problem solving for and via. Learning about problem solving is what we do at the moment. You get some information about this activity of problem solving. Learning for problem solving is training students to become better problem solvers, teach them heuristic techniques and so on. And learning via problem solving is using problem solving in teaching to promote other content. For example, learning about the perpendicular bisector via a problem and finding this concept for your own. And we're going to focus a bit on this. A typical teaching unit all around the world looks more or less like this. There is an exploration phase where a new topic is discovered. Then elaboration phase where this is systematized, where rules and algorithms are formulated. And then there is a deepening phase where this, what has been learned, is exercised so that it is memorized and used. And traditional teacher-centered units often look like this. At the beginning, there's a short exploration and then elaboration, maybe alternating a bit, but then most of the time there is exercising. In a teaching experiment, we tried it a bit differently. We took more time at the beginning of the unit to give the students a problem and give them time to work on this problem. And then we talked about the problem with them. And then they, of course, did some exercises also in the teaching unit. And to find time for this problem at the beginning of the unit, we just cut some of the exercises. And in this study, we could show that this really works. The students in this problem-based teaching do not learn less than the students in the traditional teacher-centered classes. And those students might even learn more because they learn about problem solving. And we have first hints that they might remember longer and better what they learned because they discovered it for themselves. However, this is still a challenge for teaching this problems in exploring. What are good problems for mathematics teaching? We especially need problems that fit the curricula and help teachers to teach wire problem solving instead of those matchstick problems that have nothing to do with the curricula we need to teach. If you want to learn more about classrooms in which students are highly engaged solving problems, then I recommend to you Peter Liljedahl's work of building thinking classrooms. Peter questioned every teaching norm there is and did a lot of experiments and micro experiments to see what works best. And he proposes classrooms in which students are working in groups of 3, and it's important that those groups are randomly assorted and they are working on whiteboards. So they are standing and working on a vertical area. And the students in these classrooms, they work on curricular tasks, but they are not told in advance how to solve them. So all these curricular tasks are problems for them, and they really get into thinking and reflecting about what they are doing, and therefore learn deeper than just memorizing a rule, using it, and then forgetting about it later on. So we've seen this, it's not easy to use problems, even though it's very rewarding. What else prevents us from changing classrooms to more problem-oriented teaching? And one of those reasons is what you test is what you get. If problem solving or other process-related competencies like reasoning or modeling is not part of written tests, then students and teachers will not take it seriously. And it's not easy to use non-routine problems in tests. And if problem solving is not part of centralized tests, then teachers will not pay much attention to problem solving in their teaching, but to routine procedures to train their students to be good at those centralized tests. So we really need to think about test culture when we want to change our classrooms. How can we measure problem-solving competence? In the PISA study, they say that problem-solving competence cannot be described as a unidimensional construct. At least analytical and dynamic aspects of problem-solving competence have to be distinguished if all aspects of problem-solving are to be covered. And in PISA, they give problems like this, and then a lot of questions and singular tasks regarding this. For example, a task understanding the problem, working on parts of the problem, reflecting upon the problem, and they give points to this and try to measure all these components of problem-solving competence. But in my eyes, it's still a research gap, how problem-solving competence can best be measured. And this includes heuristic literacy and metacognition and other parts. PISA offers one possible approach, measuring of partial competencies. and they use dynamic tasks. But we need to think about alternatives and need to discuss them, how to best measure problem-solving competence, not only in tests like PISA, but also at school in written tests after a teaching unit. Okay, finally, I want to shortly look at digital competencies. In a research project in Cologne, we have thought about what digital competencies teachers need. And we thought about 3 areas. First of all, the teachers need professional handling. They need to be able to use technology themselves, be it a graphic calculator or programs like GeoGebra. Second is they need to be able to use technology for their regular teaching. For example, teaching the Pythagorean theorem, they need to decide if they want to use technology or not, and if they want to use it, which technology for which actions and which activities is technology best used, and so on. And finally, teachers need to be able to teach about technology, help students to use technology for themselves, but this also includes teaching about cyber mobbing, good use of social media, and so on. But this is still a young and developing field, and we need to do a lot of research on such competencies. In this area, Mishra and Köhler extended the famous Schulman idea of content and pedagogical knowledge and pedagogical content knowledge with a new circle of technological knowledge. And then these new intersections, technological content knowledge, technological pedagogical knowledge, and here in the center, technological pedagogical content knowledge, TPEC. And this is often used in studies. For example, Valtonen et al. Address all these areas in a questionnaire to measure these parts of professional teacher knowledge. But again, this is a Likert-Scale self-report instrument, and we need to improve on this. Drummond and Sweeney use a test where participants are given statements and they should decide whether they are true or false. This is another kind of measure. And in Cologne, we try to develop other items and a new kind of instrument, because being competent is more than just having knowledge. We try our luck with open items. So for example, we asked our participants what mathematical content can be represented well in Excel. Justify your answer in 1, 2, 3 sentences. And then we code the knowledge, what they answer. 0, 1, or 2 points if they give no or a wrong answer, something Excel is not designed for. 1 point for limited usability, for example, just calculating things with Excel and ignoring that the program can also help with graphs and other things. And 2 points for a wide range of applications. And then we also rate the justification of what they have written down. If they give convincing arguments for this or that use of the program. Another example is this item. What are the arguments for and against the use of Excel in mathematics classrooms? And again, they are asked to justify this. Whereas the first question was about knowing what this program can do, technological content knowledge. This question also addresses pedagogical parts of knowledge and competencies, because they have to argue, they have to justify what they do and not just know something. And we also have questions like this. Think about this. You are planning a teaching unit for 3 to 6 hours on the topic terms and equations. Now, please think about the use of digital tools. In your opinion, which digital tools could be used in relation to your lesson? Give reasons for your answer. So this really addresses everything. This addresses the center TPEC. They have to think about their teaching. They have to use about whether or not using digital technologies and which technologies and tools. And then they have to reason why they want to do this. Does this really help? Does it make procedures faster? Does it allow the use of bigger and more complex numbers and contexts, and so on? So this is our way of trying to measure competencies of teachers. But there is still a lot of research to be done, and any of you could help improving this field. I hope I was able to give you some ideas of what challenges we are facing and what needs to be done in teacher education and especially in research on teacher education. And I'm looking forward to discuss these and similar matters with you at the conference. Thank you.